Welcome everybody, you're watching Mr. Fugu Data Science. Today we're going to do something a little different. Look at 10 real data science interview questions. Let's get into this. If you had two different fair six-sided dice, what would the expected value of their sum equal? And so you see these four answers right here, and you have to think to yourself, well, how am I going to solve this, right? What am I really being asked? So let's work this out. If we were looking at this and thinking about what the expected value of the sum would be, we'd have to figure out what equation or formula we would have to memorize. So this is what we're looking at. So the expected value of x equals the sum of x times the probability of it occurring. All right. So then what do we actually do with this? Let's look at, if we had these two die, you could look at what numbers occur on each face of these. So you have two ones, a 1 and a 2, a 1 and a 3, etc. Then you have to count how many times these occur. For example, you have a 1 and a 2 occurs 2 times. You have a 1 and a 1, which only occurs once, and you're getting the sum of these. So it'll be 2, 3, 3, etc. Right? So now we say, okay, so we start putting that into a table. And so you get one occurrence of 2, two occurrences of 3, 3 of 4, etc. until you hit this max right here. But I had these questions come up on a exam where I only had about a minute to solve each one of these. So you have to figure out, well, how am I going to solve this quickly? All right. The answer becomes 7 after you work all of this out. But how can I look at this real fast and just get this answer? Well, you have an equal likelihood of 1 over 6 for any one of these faces to occur because it's a fair-sided dice. So then you have to add up just all the different numbers that occur on this dice, 1 through 6. Then you'll get 21 over 6, which is 3.5. But you have to multiply that since you have two dice, and then now you have 7. So that's a quick, nitty-gritty way of doing that really fast. The next question that came up was, hey, let's look at finding the max number. So if I am given this function and I'm supposed to insert my code here, and I'm given these right here, I have to figure out, well, what am I actually going to use to solve this? The first thing you need to realize is you're returning the max. So this right here is useless, all right? The next answer you have is, well, I'm incrementing by 1. But the problem is my starting value is negative infinity. So incrementing by 1 is just useless. So then now you have to look at these two. You say, well, all right, am I using a plus incrementer or am I just using an equal to? Well, let's find out. So I'm iterating through whatever my numbers are and saying my number has to be bigger than whatever I'm looking at, right? And therefore, I'm iterating through my numbers list that I'm providing. And I'm saying if my number in my list is bigger than basically anything's basically bigger than this, but then I have to find what's the biggest value within that list, right? So I say, okay, so either I'm going to increment through my numbers list, or I'm going to store my new number and call that my max, and let's see what we need. If we plug it in, it turns out that we need this, and that gives us our answer. But what happens if we did the plus increment? Well, that doesn't work for us. We get our negative infinity, all right? So you got to pay attention on how this is written so you can immediately drop something. If we're looking at what algorithms are most beneficial for binary classification, we have to just think real quick, well, what is binary classification really giving us, right? It's like a yes, no, buy, sell, 1, 0 situation. Right off the bat, we could think of one thing if we're paying attention. But let's kind of look at this. We know that a binary classification is giving us in terms of a Bernoulli probability distribution, all right? Where you could have your 0, 1. And that's really good for classification. If we're looking into logistic regression, that's really good because that's giving us something that we could use for two classes. Same with SVM, but we're not calling SVM today. We also have k-means, but is that really good for doing some kind of binary classification? So let's go in here through IBM and we'll cut through the nitty-gritty real quick and we'll have to just make a few points. So when you're using k-means, you're basically trying to initialize some centers, okay? And after you're doing your first iteration, you end up coming into a situation with your distances. And because of this, when you're trying to do a reassignment you're going to arbitrarily set this up. And since you're using a Euclidean distance with k-means, you have an issue where your data isn't able to meaningfully break up any ties between distances to classify which cluster your data are going into, because you have a 1 and a 0, right? So it specifically says right here, you're ending up with a iteration that's no longer strictly an integer value, all right? And so you're going to have issues with trying to determine, like I said, what cluster goes where. So in the gist of it, logistic regression is what you want to think of. You have this weird thing called either simplex coding or algorithm, and I'm not sure what they meant by this question because I'm unfamiliar with it, but apparently from what I read, it's a type of linear programming technique focused on optimizing and used as some form of constraint. So that right there, I just got rid of that. So what is a requirement if we're looking at primary keys in SQL? We need to choose some kind of answer. So we noticed a few things that are interesting. You see an auto increment, which can be used for primary keys, but it's not necessary. Then you have foreign keys only reference a primary key. Well, that's interesting, but that's not exactly what we need here. A primary key must be unique and not null. That's what we need for our answer here, all right? While auto increment is something that can occur if you set up a primary key, it would only work if data did not already have a primary key, or your data didn't have anything useful that evaluated to a primary key. That's where you could generate your own, all right? But something that's interesting here as a side note, it says only a single column can be used, and that's not necessarily true. You can have multiple columns that spread across as long as the data does not repeat itself, okay? So this gets into something that's really useful. If you're interested in reducing high bias and a neural net classifier, how would you approach this? And you're given a few things, and you say, oh no, what do I do here? You have logistic nodes and you're trying to make them into linear. You're trying to create neural network into a linear regression model. You're trying to increase your number of hidden layers, or you need to just basically say, hey, let's chuck more training data at this, all right? Well, there's a few things going on here that we need to evaluate first. So let's give a little background. You need to, one, realize that there's a trade-off between your bias and your variance, all right? You need to consider the fact that you're always trying to generalize your model. You don't want something that's highly specific that could only work for your current training data. You want something that could evaluate to seeing new types of data, all right? So over and underfitting or circumstances we need to evaluate. So if we're looking at a high bias, it means that we're not doing a good enough job for training our model because our error is too high. And if we have a high variance, then that means that we're not accurately predicting the validation set. So the takeaway, just say, if we're overfitting, we may be only learning the current task and not generalizing, okay? So overfitting, low bias, accurate for the training data, but then you have a trade-off of high variance, which gives you a poor ability to predict. Whereas the reverse is you have a high bias, but you're poorly trained on the training data, and you have a poor ability to now predict your validation set. But then how do we start evaluating, a resolution for this? A few things you can do would be increase the number of iterations or epochs, or train a bigger network. If this was the reverse question of looking for variance, we would have looked at increasing the training data, or trying some form of regularization terms, or changing the type of model that we're going to use. So two of the problems that we had said, let's create a linear model, okay? Well, in creating the linear model, we end up creating a new problem where in turn you're actually increasing your bias while you're decreasing your variance, okay? So you end up having this issue, so you gotta be careful with that. So let's go back up to the top, and what did we want to do here? Well, since this was a classification problem, what are we doing in this? We're wanting to increase the layers so we can start receiving more information about our data to output, our classifier, because in a sense, what do we have? We had a classifier that we were looking at. So it appears that the answer here would be to create the number of hidden layers. So let's remember some of this because we'll come back to it for another question that was asked later. So if I'm looking at a window function for SQL, I need to create a time delta, okay? So how am I going to do that? Well, there's one piece of code right here that says, or a little bit of wording that's very distinct. It says row-wise, adjacent rows. We need to look at what's different between any of these. We see two of them, let's say lag. We see something that says first value. And then we just see this select. We say, okay, something's going on in here. So the first thing, if you're unfamiliar, the lag function allows you to work row-wise to access rows. So that looks extremely promising. But what is this first value? It's similar to the lag, but you're actually just, pulling from a set of values, one specific value that's, I guess, most recent, versus something you're plucking from behind what you're looking at. So it appears that we need to use something of a lag. But now we have a partition by, and we have an order by to make our decision. All right. In this case, what we need to do is we need to do the order by and not the partition by, if I'm correct. Also, I would like to mention if there's any mistakes you catch in the video, please let me know so I can make some improvements or make some notes later. Okay. The seventh question was something that deals with performing poorly. So what will we do if we had a classifier that is training well but performs poorly during your production? And now you say, well, is this a variance, a bias, an entropy, or a noise problem? Well, let's start off with the noise. Noise can contribute to issues in your analysis for your network, but there's techniques you can use to try to minimize this pre-processing before you run your neural network. Just depends on the circumstance and how much noise you have in your data, such as images, for instance, can have this problem. Now, if you're looking at entropy, high entropy, I'm assuming that they're meaning cross entropy and they're meaning a positive value. That's what I'm taking away from this as my assumption. We have to remember that the cross entropy is dealing with a probability distribution between two events for a random variable. And you're also thinking of this as like a loss function and trying to figure out how close you can get to an actual distribution. So I'm thinking to myself, well, this might not be what I'm looking for. And the noisy thing I could kind of take care of. So is this a bias or a variance problem? And so it's saying training data. Well, the high bias is dealing with poorly trained data. So let's scroll back to the top. Give me a second. So remember, the training data, high bias, gives us a poor result, and it also affects the ability of us to perform our validation set. Now we move on to question number 8, where we're looking at a support vector machine, and we're training on 2 classes, but we're wondering, what is the minimum number of support vectors we can have for this? Well, since we're not dealing with the plane, we're actually slicing our data between a line. And so the only answer would be 2 here, all right? That's the minimum that we are going to have. I'm not going to go into why, but that's your answer. Now, which best describes cross-validation? Well, this is very interesting because cross-validation, you got to remember you're doing your train test split or train test validate, and there's a few things that are going on with this. There's different kinds like the k-fold or the leave one out method that you can do. But in a gist, you're trying to avoid your overfitting. And that's what I think I would choose here for my answer. Because you're not always going to have a situation where you have a lot of data. And there are circumstances for cross-validation that account for very small forms of data. Dealing with eliminating training error was something I was considering using for my answer. But at this point, I think I'm going to say prevents overfitting. Now, if we were looking at training a model using the gradient descent and you don't reach a global minimum, well, what's one way you could resolve this? Like what's a possible reason for this? So there's a few interesting things. It says you could add a regularization term, you could switch your model and put more parameters, you could reduce the learning rate, or you could use a smaller training set. I'm not going to say this, so I'm throwing that out right off the bat. If I'm running a neural net, I want a bunch of data. So let's look into this. If you're running into a situation where you don't meet a global minimum, you have a few problems. You might not have a convex function. You might run into finding a local. You might end up finding some kind of a saddle. A way to look into this would be decreasing your learning rate. So for instance, if you're running along the horizontal, you would want to run as fast as you can. And then when you start hitting something that's vertical, slowing down. Now, if you're trying to converge, this would be a problem if your learning rate is too big. All right. Now, your convergence also depends on your initialized parameters. So that's something you need to consider too. Now, what are we really trying to achieve? We're trying to shrink the weights or the coefficients, and we're also trying to remove the higher degree polynomials. And that's what made me hesitant on this right here. So if I'm looking at regularization, I'm using a hyperparameter that I'm trying to adjust the bias. And if I'm adding parameters to my model such as weights, I have issues where I may overshoot my minima. So for this, I have to say that I would suggest reducing my learning rate in order to try to find my global minima, if there is one. Let's have a bonus question real quick. You have probability of A and B equals the probability of A times the probability of B. And which one guarantees this? Is this correlated? Is it the same event, mutually exclusive, or is it independent? Well, I'm not going to say correlated, and I'm definitely not going to say this is the same event, because A doesn't equal B. So, what does mutually exclusive deal with? Well, mutually exclusive is like your or situation, this or that, where you say either A or B equals A probability of A plus B. And that's not what I have here. I have an and. So, okay. So the only thing left is saying that they're independent. Thinking of like the intersection between them, their joint probability. I would like to say thank you for watching. Please share, like, and subscribe. And if you subscribe, turn on that notification bell. I hope that this brought utility to someone. I'll see you in the next video. Bye.